Hey everybody, tonight we're trying to find the last two digits of a very huge unpronounceable function without using this result called the totient function. This is sometimes called the Euler Phi function. In fact, it's a more common reference, I think. But this little object that you see that's behaving like the exponent here, this is called phi of n, and what it does, it counts the number of values less than or equal to n that are coprime to n. And it turns out when you raise a base to that value, you get a congruent equal to 1. Now, something, and again, I'm not going to try to prove that, but that depends on the fact that this base a, which is an integer, and the modulus n, that should be an a right there, folks, are relatively prime or coprime. Okay, so this only holds when the modulus n is relatively prime to the base a. All right. Now, again, a lot of people like doing it using this, and you can see how it's useful because one, you can see how the 431 would get reduced to a much smaller number, much easier to calculate value. All right. Now, the approach that we're going to adopt right here is we're going to look at 3 to the 431 mod 100. Okay, we're going to try to reduce this exponential modular 100. Now, I think a lot of you know why that's the case. If you divide a number by 100, the remainder is always going to be the last two digits of that number. For example, 123 divided by 100 leaves 23 as the remainder, and 23 are the last two digits of 123. Now, another way to write this is like, for example, I'll just give you a concrete example. Let's say we have 43, 71. Notice that this is congruent to 71 mod 100. Okay, and one easy way to see that is just you would have 43 times 100 plus 71. And also these digits here have powers of 10 that are 2 or higher. So 4300 is congruent to 0 mod 100, leaving just 71. So that's why we want to reduce this exponential modulo 100. Now I've started out with a few facts here. And again, we're not going to use this. Now y'all note the computation you have to do is 3 to the 5th. 3 to the 5th is, let's see, 3 to the 4th is 81, and 3 times 81 is 243. So 3 to the 5th is equal to 243, right? So the last two digits of 243 is 43. And notice we have 3 to the 5th is congruent to 43. This is all mod 100. I just write it down one time, okay? Now, the nice thing about congruences is you can treat them just like equalities in most cases. So if I square 3 to the 5th, I get 3 to the 10th, but then I get 43 squared. Well, here's another computation you would have to do. 43 squared is 1849. So you would have to do that by hand, no calculators. You would have to do that by hand to make this legitimate. 43 squared is 1849, but notice that's congruent to 49 mod 100 because you have 49 as the last two digits. All right, so what we have here is 3 to the 10th is congruent to 49. Then we're just trying to get a higher and higher power that's going to be congruent to 1, and that happens on the very next step. 49 squared is 2401, and y'all, what did I do? I squared both sides. If you square this, you get 3 to the 20th. If you square 49, you get 49 squared is equal to 2401. I put this in red for a reason. So now we know that 320 is congruent to 1. Now that's without the help of the totient function. Now y'all, by the way, the totient function would have returned 40 and you would get 3 to the 40th is congruent to 1. But what we have going on here is something that's a little bit better than the totient function because we can, by laws of exponents, notice that 20 times 21 is just 200 or 420, right? So 20 times 21 is 420. All right, but that leaves this 11 that you see right here. But you can see why we wanted to do this, right, folks? Laws of exponents and the fact that 320 or 3 to the 20th is congruent to 1, right? So this is literally like saying 1 raised to the 21st power here. Okay, now that's nice, right? It's just 1. So all of a sudden, we've reduced it to whatever 3 to the 11th is. We've started with 3 to the 431st power, and now we have to do is do a computation for 3 to the 11th, all right? But we already know, well, let's just keep going. So we know that 3 to the 431 is congruent to 3 to the 11th. I've just cleaned this up a little bit, okay? Now we can rewrite 3 to the 11th as 3 to the 10th times 3 to the first power, right? Put a 1 there for emphasis if you want. But notice we already know what 3 to the 10th is. 3 to the 10th is congruent to 49, right? But 3 times, this is 3 times 49 right here. 3 times 49 is 147, right? And of course, 147 conspicuously has 47 as its last 2 digits. And so this is the answer, ladies and gentlemen. We have shown without a doubt that 341, 3 to the 431 is congruent to 47 mod 100. And remember, what's the purpose of doing mod 100? It gives you the last 2 digits, right? When you reduce it all the way down to a number between 0 and 99. So this is mod 100, okay, and 47 is the last 2 digits. The last 2 digits are 4 and 7, however you want to say it. Last 2 digits, right? Okay. So let's go back up here. The last 2 digits, 47. And again, folks, what I like about this is you don't have to use this Euler's Totient Function to get the job done. So this is the answer. Hopefully I included enough steps here where it made sense. And again, I want to be honest, we had to, this 43 squared would be something you'd have to do by hand. 49 squared would be something you have to do by hand. But after that, all the computations are easy. So we accomplished the solution here without having to appeal to this very famous result, you know, or even know what it means. But y'all, by the way, just, I will go ahead and write down right here, even though we didn't use it. Phi at 100 happens to be 40 because there are 40 numbers between 1 and 100 inclusive that are relatively prime to 100, but that's equal to 40. And one way to, you can also, the calculation on that, another way to calculate it is just to take the 100, and this is something you will see in a number theory class. You do 100 and then you go, the only 2 divisors of 100 are 2 and 5, right? 100 is equal to 4 squared times 5 squared. So the only 2 prime divisors, the only 2 divisors of 100 are 2 and 5. So what you can do is you can do 1 minus 1/2. And again, I'm not going to prove this one for you. It's a little bit harder. This is 1 minus 1/2. And then 1 minus 1/5. Okay, believe it or not, if after you do the arithmetic on this, you'll see this is another way to do it. Again, you can do the arithmetic on this. This would be 1/2, 4/5, and then you can see how 40 would work out of that. That's a little bit easier than having to list 100 and list all of the values that are coprime to 100. But in any event, we didn't have to even use this. We discovered that 3 to the 20th was congruent to 1 just by standard routine modular arithmetic. All right, that's all. Thank you for being.